Thank you so much for coming. Okay, we have all our guests ready. And myself, Adarsh Jain, I have 13 years of industry experience in GPU and HPC. Often I've been asked as to what do you do, right, by my parents or relatives. I told them in very simple language that I save time. Okay. So if there is something that has to be done in 1 hour, that is happening in 1 hour, I try to do that in 1 minute or 10 seconds if you have a lot of money. Okay, so that's I think what connects all of us. We are here in different. We are from different age groups. We have different. I mean, there are GPU developers. There are developer people. There are managers. There are entrepreneurs who are owning the businesses. So, but every one of us is connected by the technology of GPUs. Okay, so I'll just give you a heads up as to what we're going to do here in next 3 hours. So we have 4 sessions. First is the speaker session. We have all the speakers here. Second is the podcast session. Second is the tech dialogue that I'll be taking. We'll know what GPU is, what are the components of GPUs. Third is the podcast session where I'll be asking our guests their journeys about GPUs. Fourth is going to be a poster session. We have arranged we have arranged some people from our company who will be telling you as to what they did to solve a particular problem via GPUs. Okay, so I'll call upon first guest speaker who is the co-founder of this company. He has 18 plus years of experience. He is a IIT Bombay alumni, 45 plus patents. Okay, he has done what it takes to be here. Please welcome Mr. Gaurav Tripathi.
Thank you. Thank you. As Adarsh already said, it's really good to see people leaving all other plans on weekend, maybe watching a movie or going out with family, and leaving all that apart. You are here on a Saturday afternoon, so that itself says a lot about interest, about who you are really. So thanks once again for coming all the way here in Ninjawadi now. Yeah, we were actually asked that in the session, why are you doing it in Ninjawadi? Why can't we have it in city? Ninjawadi still is a part of Pune. Don't treat us like this. But yeah, we knew it is a challenge to come all the way here. But yes, thank you, and hopefully the team has been speaking to a lot more people. They said there are a lot more people who said we are on the way. Like yeah, that makes us feel even more that yeah, Hinjodi is really far. Okay. I'll be take this. So before I start, I have an honest admission. Slides which you will see, except 2 or 3 slides, all of the slides were generated by AI. Yeah, I just gave maybe 2 lines. Yeah, that this is what I have to present and this is what it should cover. All of the slides got generated. So this is where I love AI. Yeah, and, all of it. What I'm going to cover is just a very high level. How GPUs have been really being used in healthcare specifically. What are the kind of problems? And inadvertently, when we talk about problems, yes, a lot of it is going to be from our own experience, what we have been doing. Hence, we can speak about it. I have tried to include more things, so use cases which even we are not working on, but still that's where GPU is being used. If you have any questions after the slides, please feel free. I'll be happy to answer any questions. So I love this because I think I always had this challenge to explain to people, यार GPU में ऐसा क्या है? Now why GPU? What so यार ठीक है सब कुछ तो है सर्वर्स हमारे पास CPU ये वो सब तो चलता रहता था GPU से क्या हो गया? So then I used to show just this. This is the difference which really came after GPUs. You know, like earlier, everything that was happening at that snail's pace. Yeah, literally, wherein we have seen cycles where if we wanted to do something, either it was straight away said impossible, or we used to get an answer, yeah, we'll get something in 2 weeks, we'll get something in a month. ये तो एक साल लग जाएगा. It's not possible, right? And all of that, once we have the GPUs, it's really blazingly fast. Healthcare, so this example, again, my laziness, it's covering only US. The stats are around US, but given the pole position that US is the largest economy and so on, I think that kind of says that we can generalize it in a way that if US is looking at reducing the costs around $300 billion, 450 billion, that's the kind of thing, right? And just if we look at the R&D and improving trial operation, that is just one part of it. Overall in healthcare, there are massive savings that US is looking at, and hence I'll say all other countries, everybody should be looking at their healthcare is going to be insanely expensive, really. As we move, and in fact, post-COVID, there are already studies that what COVID has done to our body, probably we'll come to know in next 5 years, right? And hence the healthcare costs are going to go up, and that is where there is a need, all-time high, where we need to innovate in healthcare, because otherwise we are really looking at a situation where we won't need another COVID to crash the healthcare system. There will be just some other diseases and something happens, and we'll see these crashes more often. And there is ample conversations, research, going around. People are already talking about that. Yes, crashing a healthcare ecosystem or healthcare system is a lot easier than all of the policymakers had ever thought. Just around GPUs, so GPU in healthcare and around. So 2014 was the first time there was a talk around mammography screening for breast cancer, right? And then it was the DGX AI, DGX. We do have a couple of DGX here, DGX 100. So DGX came in, and that's where things started moving further. And 18 was the toolkit itself, Clara. Now, Clara is not just medical imaging, there is a lot more that Clara already has. Clara is the toolkit that NVIDIA has, which works on NVIDIA GPUs. And then 2020, we came across where NVIDIA had spoken about the conversational AI for radiology. So just few milestones which have happened. The major areas of impact that we see and where GPUs are going to help, or AI is the obvious one, right? And I think that has three as well. The impact is more going to be because of AI rather than standalone. So AI itself is there, and biggest thing where we have already seen a lot of progress, medical imaging and clinical decision support. So these are the areas where pharma already has been using, hospitals already have been using GPUs extensively. Next is medical devices. Medical devices, if we see the innovation kind of had plateaued. If we look at the progress in the medical devices in between this thing, about 3 decades back and what we had a decade back, most of the systems simply, there were very, very marginal incremental developments. Okay? But in last 5 years, what we have seen, and now the devices which we are about to see in next 5 years, there is a there's an order of magnitude of jump. Why? Because earlier simply the devices did not have that kind of a computational power. Now with GPUs, with the devices, there is a lot that you can do right then and there. You won't need to even send all of that to a server somewhere and wait for the response and do some computation. A lot can be done then and there. Right? That is going to be a paradigm shift, and that is what we see already. The wearables, right, around, but whether it is ultrasound, like ultrasound, I'm sure all of you would have visited. Ultrasound used to be, bulky machines, size came down. Now we are talking about really handhelds, just these small devices, right? And the quality of output of those devices is far superior than all of those bulky machines that we have, right? This is hyperintelligence. Okay, so digital pathology scanners, again on medical devices. Our favorite area is drug discovery. That is where we, as a company, we work a lot. So drug discovery, again, a lot of the problems which people used to talk about, that maybe these are impossible to solve, and there used to be really very credible, very big scientists who used to say that there are certain problems which definitely can't be solved at that scale. It's simply impossible. Because now with computation we see, right? It's whether it is on the molecular simulation side. So simulations, for example, there have been cases where simulations used to run for like months, literally months. Right now we are talking about things wherein yes, things are the same scale of things. They are happening like within a few hours, right? And there are which are being done in a few minutes. Something which used to take months is being done in minutes. Right? So simulations, protein folding, extremely complex operations, understanding all of these diagnostics. So diagnostics again different. So diagnostics part on the devices side, and second on the actual analysis. How do you analyze those images? How do you do that? So there we have already seen that the assistants, AI assistants, which are coming up, whether it's radiology or so on. With every diagnostic, now there is the data that is being generated. There is a lot of automation which is going to come. So, given the load on a typical diagnostic center, right, it is more because the amount of data that they can process, and in the end, it comes to the people manually doing something. A lot of that is going to go away simply because that kind of computation will be possible. A lot of things simply can be automated because that kind of a, let's say in diagnostics, the computer vision, right? The computer vision problems, right, where you don't need a human to. This is going in, I need to change settings. Sorry for that. Okay, so where we can simply have. Or we don't need to have any human in loop. It can just go on. It can read the reports automatically. It can tell you what's the summary. It can tell you what's the next step. Right? You don't need a human. More examples specifically around AI. What kind of AI? So whether it is genome sequencing, protein engineering, property predictions, molecular documents, so tons of examples. And all of these, again, it's not that these things were not done earlier. Everything was done. Bioinformatics has been there for decades, but the kind of acceleration which now is possible with GPUs it's insane. Drug development. So that's again one of the areas, the core area where we work is drug development. Like why we need to solve it, and where we really see the impact of GPUs is huge. Simply because of the scale. Just one drug, the time that it will take for it to come out to the market, right from the early stage research, drug discovery, to the market, it can take anywhere between 6 to 12 years or more. And in terms of the money, anywhere between $1 billion to all the way up to $2.5 billion, right? And all of it, of course, at each stage we see the kind of computations and the things that you are talking about here. If we look at this is in fact still at a drug discovery end. There is stage even before that where you start with 250,000 compounds, right? So you can imagine if you have to go through 2.5 lakh compounds, chemical compounds, of course, why it is expensive and time taking? Because right, most of it's being done manually. Somebody has to look at it in the lab, go through the reading, understand, go to the literature, and then say whether this will work, not work, whether this is toxic, non-toxic, and so on. All of it. All of that, if can be done at scale, it reduces the time at each stage, whether it is the clinical trial stage, the amount of time, so you can see 6 to 7 years, the money, and everything. Right? And finally, even in manufacturing, we are talking about how we can accelerate all of that. Right? And again, COVID taught a lot. COVID in itself became a project wherein, yes, the pharma was able to break the barriers. Right? Healthcare was able to break the barriers. Right? The regulators, for the first time, they had to give emergency approvals to certain things based on limited data. But then we see that, yes, why can't it be done for other drugs? Right? And that's where regulators are also open. Fine, give us, don't just push data onto us. Help us make those decisions, and we'll do the job. And just a visual representation, all of it, that the different kinds of problems that we are looking at, whether it's clinical trial optimization, healthcare, drug discovery, there is a lot. Everywhere you see, and literally every element of it, GPU is going to touch. Very evolved, very specific problems. So whether it's a new molecule design or target identification, target is like you identify if there is a disease, if there is a drug, where it should really act, right, inside your body. Clinical trial, so we are able to predict clinical trial with very, very high accuracy now in terms of that we can already tell whether before starting the trial itself, we can tell you whether this trial on this, if you plan to go by this checklist or in this way, whether that trial will succeed or not. Right? Then it's like instead of throwing darts or instead of shooting in dark, you have some way of figuring out, okay, which one to prioritize, which one to maybe just hold on. Drug repurposing, again, very interesting application. The same drug, you take it and it's been there for market for one type of a disease. Can you use it for some other disease as well? Right? And the most famous, infamous example that is for drug repurposing always is the Viagra. Right? It wasn't made for erectile dysfunction. It was for a completely different area. And then it was discovered that, and then that led to a massive market, right, for it. And now there are tons of examples, and every pharma company is looking, because there you save money, and that if you save money, ultimately the cost of healthcare goes down, right, in the end. Devices, so these surgical robots we have already seen. In fact, in Pune, in hospitals there are now smart hospital beds, wearables. I'm sure almost all of you would be having already. This is something which is internal, something which we have achieved. I think so. Exome sequencing, around, it used to take like 60 to 100 minutes per sample. We just ran it on RTGX, was done in 5 to 6 minutes. Something which was earlier happening in 2 to 2.5 hours was now it's happening in 11 minutes. Right? So if you look at this, imagine just multiply this by 1,000 or 100,000, you see the scale. Something which we were supposed to do it in months or a year, now will be happening in just a few days. Right? So that's the impact which we ourselves have been able to create using diagnostics. I think I already spoke about. So there are already diagnostic modules, whether it's MRI, CT, almost everywhere now. GPU is going to be used in some or the other form. This is again more promotion from our side, just to tell everybody that yeah, what do we do? So different kind of problems on the drug discovery, all of it we have been working, and everywhere, almost everywhere, the push has been: can we accelerate this further by using GPUs? Like whether it is on biomarker identification, like or simply scanning through all of the data and generating insights from it, textual data, imagery data, and all of it. Yeah, that's it from my side. How much time did I take? A lot more than what was allocated. No? Good? Okay, thank you then. These are, by the way, the DGX. I took the selfie with the DGX. We are very much here. So, yeah, we have two DGX which we got long back. Took us a lot more time to make it work for us. And now we are in the process of procuring 5 more very soon. And that's why we see, if not for DGX, all of the work that we have been doing, if not impossible, it could have been simply not feasible. Because if the team came and told us that yeah, we'll do this, but we'll take 9 months, we say okay, forget it, it's of no use. So, yeah, thank you.
Thanks, Gaurav. Any questions for Gaurav? या तो सब समझ आ गया है या कुछ नहीं है.
What are your thoughts on the future of computing? GPUs are the same.
Yeah.
As you said, right? We have some computing that was required here. People brought down to let's say 1 or 2 days. What is the future?
I think everybody is talking about quantum. But yeah, before we latch on to quantum will take time because quantum computing will work only on a very limited set of problems. And as with every technology, even GPUs, when they came up, it's not that we are able to right away start with GPUs on all kind of problems. The stack will need to be prepared. So before quantum, I see tremendous innovation around GPUs. We already see. So earlier there was practically no competition to NVIDIA. Now the competition also is coming, right? And that will again push for more and more innovation. So we are going to see many more interesting models to come around. In fact, FPGAs are already hot. 6 are already hot. So there are just hardware innovation itself there's a lot that is happening. Anything more? Anybody? Yeah.
My question is, some weeks before, Microsoft announced that they had the GPU design. They also designed regarding something bigger. So again, it's again we want that there will be lots of GPUs are coming. But the basic question is that how GPU improves any, let's say any AR, any algorithm running. So that is still where that needs to be going.
Very simply, the experts are sitting here actually, but if I have to really think in terms of a layman, it's as simple as that with typical computing model has been sequential largely. We know that yeah, we saw multi-core processing and so on, but still it was not to that tune where you can really take something off the shelf and you don't have to worry about how it does, right? But execution happens in parallel at scale. That is what. So, like for example, GPUs, if we talk about it, each GPU has thousands of cores. While we talk about CPUs, we have been saying what we have been maximizing are quad core. right? So you have to see that the amount of computing itself and amount of computing that you can run in parallel without worrying about yourself how to make it. I think that's the key.
We do have a session so with quantum, right? You will require new set of hardware, right? So this then the GPU investment will become redundant. So
GPU investment will be redundant in just 3 to 5 years. Any GPU which you see the life cycle, right? 5 years is the max. And Nvidia itself will have has like end of life after 5 years. But business wise, if you see the same GPUs, in all likelihood, even after 3 years, you yourself, your team will not say, "Nahi yaar, ye kya, kis pe kaam kar raha hai?" Right? 3 years, because the innovation is happening at such a pace that the same GPU will not be that effective just after 3 years. So there is a lot more before quantum.
Gaurav, what do you see in terms of like future where the architecture of GPUs itself, the hardware itself, shaping towards solving very specific set of problems? In the sense I see nowadays GPU architecture is aligning with say models which are transformer based, or say other systems. How do you foresee these things coming in?
Purpose built and very specific task oriented hardware that we see. So traditionally ASICs have been there on that space, but I think GPUs itself, given the scale, are being tried out. Like for example, certain optimization at the hardware level, I'm aware of already that is happening for certain problems that we see. It's all driven by market. Like for example, why GPUs are being tuned specifically for LLMs, because it simply threw up a huge opportunity. Same we are going to see in few other areas very soon. There is already a lot of talk around the imaging part. There is a stack already which is purpose built for imaging. So we are going to see like all of the larger areas as again played by market dynamics. Larger the market, somebody will come up with a specific architecture for that. Okay, thank you.
Thanks, Gaurav. So you guys need to ask questions. Okay, this is not a sponsored event, and we are also not saying that we know everything about GPUs and we have it all. We are just saying that we are providing a platform where we are open to questions and we can look for solutions together. Okay, so please ask as many questions as you want, and like we also have the sessions where you can speak to the speakers, on personal basis also. So next, I would like to welcome my dear friend Rushabh Goradia. He is a IIT Bombay alumni, and he is Dr. Rushabh Goradia. Yeah, he has doctorate in graphics and animation, more than 12 years of experience in designing and developing GPUs and HPC-based applications, and he's been consulting a lot of companies. He is currently a CTO and a technical director, and CEO of Synthreads Computing. Please welcome Mr. Rushabh Goradia.
Thank you guys for inviting me here. Thank you, Innoplexus. I will keep my session brief. All of you covered quite a lot about GPU in healthcare. So there's like an off-topic where we cover about what is the impact of GPU in the defense. Synthreads Computing is my startup, which I established in 2019. And we have been working closely with the defense forces. We have been giving turnkey solutions to the Indian defense. And GPUs have been playing a pivotal role in most of our products. So through this presentation, I will briefly go through my own journey as to how I have worked on the GPU or different problems, and then culminate on how we have been using GPUs these days for solving the defense-related problems. So we are located in Pune, and yeah, so more details in the upcoming slides. So I started my introduction to GPUs while I was doing my PhD. That time in 2007, CUDA, that is Compute Unified Device Architecture, that was one of the technologies introduced by NVIDIA way back in 2007. And I've been using GPUs since. So before 2007, GPUs used to be specifically used to solve graphics related problems. Their hardware model was designed such that you can have realistic renderings to be done at real time, and you increase your frame rates. There was something called as shader units, and you used to code up these shader units with the RGB pixel values, what you see. And programming those shader units was very difficult. So when CUDA was introduced as a tech, it became much more easier for a coder or a developer to write their code and scale it up and parallelize it using the GPU architecture. So that helped me tremendously in my PhD. I mean, some of the results what you see here are from my thesis, and I used to work on point clouds. If you guys are aware about what point clouds are, they're like there are like millions and billions of points, and you want to render a scene in real time with realistic lighting effects and reconstruct the surface. So that itself is a challenge. And intuitively, if you think about it, then this entire operation can be parallelized, as you can work on each individual point, compute the values of each individual point in parallel. So that's something where GPU played a pivotal role in my PhD, where you used to achieve, this graph here shows the kind of speeds you used to achieve, in terms of time taken in minutes. And you can see the orange one represents the GPU bar, while the purple one represents the CPU timing. So as the problem became more and more complex, you can see the scale up of GPU as to what was the kind of advantage we used to get at that point. If that time, since CUDA was just initially introduced, there were a lot of issues as they were also testing it out. NVIDIA was also testing out the new tech, but still, it was much better than the multi-core CPUs what we used to have in those days. At that time, I used to work on singular GPUs, and eventually, once I completed my PhD, I went into healthcare. I was in healthcare for about 7 to 8 years. I was a product lead and a tech consultant at Sun Pharmaceuticals. And we used to work on preclinical stages of drug discovery, wherein we used to identify histology features initially using image processing. And once in 2014 and 15, when deep learning took off, then we used to write algorithms in deep learning and scale it up on a cluster of GPUs instead of a single GPU. So there were stacks of AI algorithms we used to run on multi-resolution images. And these images were pretty huge. It was like 1 lakh cross 1 lakh pixels, and it was multi-resolution. So you can imagine the amount of computation to be done. And on CPU, if I used to run my stack of algorithms, it used to take about 8 hours, which we almost achieved almost about 500x speed up on that, and we used to run our algorithms within a minute. So, when you speak about scales, as Gaurav also mentioned, this thing is something which really emphasizes the importance of GPU in the industry. So, from healthcare and using GPUs on clusters, I moved on to GPUs on cloud. I was a technical director in one of the companies in New Zealand, Lightspeed Graphics, and we used to provide a modeling and a rendering platform for the designers on cloud. So, you take up your laptop, sit in a cafe, and you log into the system, and you can actually render realistic scenes at real time using any computer. So the entire backdrop of computation is done on the cloud, and you just get the final display at your end. So this scene, what you see here is a rendered scene. It's not a realistic scene. It's not a real scene. And we had designed a system where you used to drag and drop. This was an interior designer application, so we used to drag and drop the furniture items. And on a click of a button, it would use to render the scene realistically. So something like this cannot be thought about probably a decade back. or a couple of decades back that you can do this in real time. But this is something what the GPUs allowed us to do. So this was one of the applications in interior designing, but then it was open for all designers, all kinds of designers, be it like you are a character animator, or you are a SolidWorks designer, or you are an interior designer. It used to allow you to render the scenes in real time. So after a brief stint there for a couple of years, I came back and I started my venture in 2019. Here we majorly focus on GPUs for defense, and I was joined by my co-founder Colonel Shantanu Roy. He's a retired army veteran with 23 years of experience, and we are a team of about 20 people, out of which there are about 5 to 6 people working in this domain of GPUs and AI. Here we use GPUs majorly for on the edge computing. So we have moved out of clusters and cloud, and we are now focusing on the edge computation. The idea being that we provide turnkey solutions to the soldiers, and the soldiers want to perform certain computations on the field, and you want the results to be seen real time. So the soldiers generally work in areas which do not have any internet. They are on off-border areas, or Naxalite areas and so on. And if you don't have internet, you cannot connect to a cloud. You cannot carry your cluster over there. So you want small devices which can give you the power of GPUs at real time and perform these computations. So that is what we specialize on. We basically use a lot of electronics. We develop our own radars, our own antennas, microcontroller systems and stuff. And these systems, they scan the environment, they generate that kind of signatures and data, which is given to a AI backend engine. And the engine makes sense of what the data is and provides a really easy user interface for the soldier to understand the environment. So instead of going on an abstract level and giving you an overview of what GPU can do in defense, I will walk you through a couple of our products, what we are working on, to give you a realistic practical example of how it is being utilized. Okay. So this is one of the products we are working on, minefield clearance using unmanned ground vehicle and AI. So there are a lot of minefields in and around the Indian borders, and many a times it happens that we have to clear a certain minefield for various reasons. Say, for example, if India wants to invade the neighboring country like Pakistan, during the time of war, then there are various minefields which are there around the borders, and you want to breach through the minefield and enter the enemy territory and then launch your attack. Clearing the minefield is very important strategically, because the quicker you clear the minefield, the quicker your infantry, your armored vehicles, your tanks can pass through. And if you don't clear and you waste a lot of time, then the enemy will have that advantage. So how can you quickly take certain decisions on the field to clear these minefields off and launch your attack on the enemy? So that is one of the products what we are working on with the Indian Army. So this is a glimpse of those products. So what we see here is a unmanned ground vehicle. This is the actual demonstration of the vehicle here. There is a forward scanning sensor plate, which has a lot of sensors, from ground penetrating radar to metal detector to explosive vapor detector, FLIR, thermal cameras, and so on. It's basically scanning the ground in front as the vehicle is moving. So the idea is you scan the ground, you take the signal signatures what are there from these sensors, and you give it to an on-edge Jensen cluster, which is there on the vehicle itself. It has to process all the requisite signal signatures and make sense out of it before the vehicle reaches that area of the ground. Because the vehicle is not stopping; it's actually continuously moving, and you want to make sure that when the vehicle reaches that area, you want to make a decision whether the ground is safe for the vehicle or not. Else the vehicle will blast off. And in case you find a mine, then you stop and you basically mark that location so that the soldiers can excavate the mine very easily. So this allows the soldier to, at least they basically do not endanger themselves by going there. At the same time, the current techniques what the Indian Army follows is pretty much primitive to clear it off. And this basically, utilization of AI with GPUs on this particular topic, on this particular product, gives you that tremendous computational advantage and the strategic time advantage, what they do not have today. So today they take about, to clear a kilometer wide minefield cross, say, for a lane to pass all the vehicles through about 6 odd meters, they take about 3.5 hours, whereas we are attempting this within 45 minutes. So we are well way on that. I mean, we have conducted about a couple of trials with the Indian Army and it's going on pretty well. Trying to reduce the timing more, but this is something which is feasible only because there are GPUs on board on the vehicle. So this is one practical problem what we are attempting right now, and this is something of a tremendous advantage for the defense forces. Just to give a glimpse of a lot of tech which is there on this product. We spoke about some sensors which are there in the forward scanning. This is just a picture, so this is not our product, but this basically gives you a gamut of all the technology used together, and how multidisciplines come together to create a turnkey solution for the Indian defense. So there are a lot of sensors, including the ground penetrating radar, metal detector, EVD, mine marking systems. Then for the robotic vehicle itself, we are designing it autonomously. So it's loaded with lidar. It's loaded with terrain viewing with a video camera. It has thermal cameras on top of it to sense the terrain around it. It has an AI engine which is running on Jetson. The pilot to handle the UGV. There is a main control unit, a power management system. There's a robotic arm system, and the vehicle movement, the robotic arm, and the scanning system. All three work in tandem together to make sure that all the typings are synchronized and the vehicle is moving seamlessly. There is a real-time kinematic GNSS communication system which is transmitting the data and the results and the view of the terrain back to the soldiers who are sitting about 2 kilometers away from the minefield. Then there is a manual override control. There is a map system over here which is visualization of the results. There's a defense series map integration and the UGV itself. So a lot of small modules coming together to get this product running, and GPU plays the critical role in this entire operations. This is another project what we have deployed. This product was with the Indian Air Force, where you have radars established by the Air Force across the country, and they are tracking your flights. These radars have been installed 50s to like 2020s, and each of these radars come up with different technologies of scanning. Like it's generally the regular radar technology, but there's a difference in the measurement errors when you look at radars from 1950s to 2020. When all these radars are scanning the same flight. Say, for example, a flight is being scanned by 2-3 different radars in the vicinity, and these radars are from different eras. They come up with intrinsic their own measurement errors, and this data is then given back to the control station, where the same flight, which is being scanned by say multiple radars, it's shown as 2 different flights. When you try to combine the data together, so you really don't know that whether you have one flight which is going around and there are 2 flights, or possibly if it's scanned by 3 radars and 3 flights. If you look at the formation of attacks from the enemy, there are close moving aircrafts which will come in, and at that time this data becomes much more important or critical, because now you don't know how many aircrafts are coming in, whether there's a singular aircraft coming in or multiple aircrafts coming in. So this was a major problem with the Indian Air Force where they could not make out how many flights are there. Secondly, due to the measurement errors, the position of the flights were off sometimes by as much as 2 kilometers. So now if you want to attack and pinpoint the flights, then it virtually was impossible. And the pilot had to decide on runtime in the air to lock the targets and then attack. So you would not have control stations on the ground which can tell you exactly that this is the flight where, and this is the position of the flight. So this was a major problem in the Air Force, which was there for a few, until we gave them a solution. So here we worked on the cluster of GPUs, wherein we installed this cluster inside the premises, which took the data from various radars and it applied AI with filtering algorithms. You must have heard about Kalman filters used in ADAS these days, or particle filters and so on. So that was combined alongside AI to give the solution so that these errors can be corrected and exactly the right flights can be indicated. So the accuracy was improved quite a lot, and this was installed at a couple of their installations. It's currently under trial now, and if possible, then it would be installed across the country. So here too, since the flights are moving at tremendous speed, you want the results to come up at real time, and that is where GPUs still play a major role in making sure that you are getting these results as quickly as possible. So these are a couple of practical problems what we have been working on. In terms of the business vertical, there are lots of products what we work on and utilize GPUs. I won't go into those details today, but you are most welcome to visit our premises and you have a look. So we work heavily in military navigation that utilizes a lot of power of GPUs. AI, obviously, it has been a part and parcel of it. RF and embedded, that is our core area where we work on, where all the signal signatures which cannot be interpreted by soldiers can be given to an AI engine which interprets it and makes a very easy output based, a very easy output for the soldiers to interpret and learn the environment. We are expanding into free space optics and quantum these days. So we have a few GPU servers at our premises, a fully equipped electronics and RF lab and a photonics lab, and a few software licenses which we use to make this work. So yeah, so you guys are most welcome to our premises, and any questions you have or you would like to have a discussion, I'm available through this meet and possibly later as well. So thank you so much once again for your time, and I'll keep it. Thank you.
Any questions? Please go ahead.
First question for the
So just 1 second. Yeah.
What is the range for that minefield device what you have created? So how much range can cover in one room?
Range as in the vehicle.
Yeah, vehicle
movement.
Vehicle is moving.
Ah.
So how much long? So it might take the minefield is either 10 meters or 20 meters like that.
No, so we are detecting mine within a distance of a meter. Yeah, because the vehicle is about 3 feet cross 5 feet, the 5 feet length and 3 feet wide, and it's actually scanning the ground right in front of it. Right, so the technology what we use, the ground penetrating radar, it needs the air coupling, the air to soil coupling has to be minimal for that purpose to happen, because the electromagnetic wave, the waves, they have to hit the soil and they have to come back and you have to collect the echo back. If the air coupling is much more, then possibly the results are not that great. Right, so, thank you.
Any other questions? Please go ahead.
Hi. My name is Pratyush. Thank you so much for a very wonderful presentation. We got to know a lot about how AI is being used in the Indian Army as well. That was really nice. But a follow-up question on that, like the model that is there sitting on the Jetson device, is it like a multi-modal kind of situation, like you have a lot of sensors coming in data? So there is computer vision also going on, because I did not see a camera sensor.
Yeah. So there is a this is just a pictorial representation of the scene, but yes, there is a camera which is there, and we do have a data fusion approach to the entire. Because there are lots of sensors around. You want to check what is the output of the metal detector along with the GPR, along with thermal camera which is installed there, and also the explosive vapor detector. So you combine all these outputs together along with the information about the location, so that the scan area should be pretty much the same for everything. And once you combine the outputs, then there is a hierarchy of models which we have implemented. So some sensors gain certain importance depending on the type of soil conditions. Say for example, the electromagnetic waves, they do not work very well in very wet soil conditions. So at that time, metal detector is more prominent. Thermal cameras are also used. But when you have very dry soil conditions, then GPR becomes the primary sensor. So depending on the soil conditions, we have an interface for the soldiers where they can select the soil where they are moving the vehicle. And
so these are not predictive models per se, but these are like threshold models.
No, these are predictive models. They have been trained extensively. So we go ahead in the site, we collect the data for months, and we have tuned those models up. And now they are tuned enough to understand, but there are different models as per the soil conditions, because it's an inherent physical limitation of the waves. That, say, for example, if you have an EM wave traveling through a wet medium, it disperses and you have a very less echo which comes up. So it's a physical limitation. It's a limitation of physics which is there. So you have to deploy another type of approach in those soil conditions. So these are tuned models, these are predictive models, but there are multiple models as per the soil conditions they work around.
When you talk about a Jetson cluster there, so there are a host of Jetson devices sitting on the platform. Like, it's not just one Jetson area or something like that. It's a
right. I mean, like each Jetson is doing a certain task. So they are not interconnected, but they are doing a certain specific task.
And you also talked about that it's like 1 meter ahead it's looking at. So there might be some latency. Like the latency would also need to be optimized in a way. Like if your vehicle is moving with, let's say, 5 meters per second or something like that, so you need to have certain amount of latency as well.
So it's we don't need a latency, but the vehicle speed is in synchronization with your scanning and the processing speed. So you have to scan the ground. It takes up a few nanoseconds. It's very quick, the GPS scans and stuff. You give that output to your Jetson cluster. It processes. That process happens in a few milliseconds. The vehicle, the distance between your forward scan plate, which is there, and the vehicle, the distance to be covered the distance to be covered should be more than the processing time what has been taken in. So if it takes, like, say, 10 milliseconds to compute, then the vehicle wheels should take about more than 10 milliseconds to reach that place to understand whether there was a mine or not, else it will stop. So all these three systems, they work in tandem to make sure that. Also, there is a robotic arm which I did not get into, but the robotic arm is a very complex structure what we have developed. It's a completely modular system, because one vehicle is scanning about 2 meters horizontally and about 1 meter in front. So when you are there on a terrain which is like a semi-desert terrain, you might encounter a few bigger stones, bushes, boulders, a few trees, very few trees. So when you have to move such a UGV over on such terrains with a 2 meter span, which is about close to 6 feet, it becomes a lot difficult because of these obstacles which are there. So we have created a modular structure on the entire robotic platform, which divides those 2 meters into 50 centimeter plates, which are the cassettes. And the robotic arm is itself like our fingers, where you have 4 independent projections of the arm, which, say, for example, if there is a stone here, that plate lifts itself up and comes back in, so that you can still scan with the remaining 3 plates, but the 4th scan does not happen because there is a sheer big stone there. So that robotic arm itself is a very complex structure, and synchronizing the robotic arm movements, along with making sure that the plate is as close to the ground as possible because the terrain itself is uneven. You can encounter huge gradients when you are moving. The terrain is uneven, so if the vehicle is tilting on this side, the arm has to make sure that it is still parallel to the ground. The plate is still parallel to the ground and scanning. So that technology itself, synchronizing that tech along with the vehicle movement, the processing, and the scanning itself is like a complex system in itself.
And
So a lot of
just
computation.
a curious thought there, like you talked about robotic arm, so there might be plans to excavate the mine also in an unmanned way, or like right now you say.
There are plans, but right now what we are doing is we have a marking system. So there is an infrared paint which is thrown over there, and this is generally a nighttime operation conducted by the army, so they don't do it in daytime. So we basically spray the paint over there, and the soldier comes in quietly, and they have these sticks which they have a drill. They know the drill to excavate a mine. So they go around and excavate the mine. So by the time the vehicle is moving ahead, there would be a few soldiers following it at a certain distance, about 50 odd meters from the vehicle. And once the vehicle is marked something, they see it on their tablet that there is a mine which has been marked, so they go ahead and excavate it. But yeah, there can be plans to excavate it later on automatically as well. But that would require certain surgical precision because few of these mines, they come with something called as tripwires. And you must have seen in some movies where, there's a wire and when you accidentally pull the tension, then the mine blasts off. So those things you need to detect and also surgically make sure that the tension is not released so much that the mine will blast off, that the soldier knows. So coming to that level of precision possibly, which is there in medical these days, we'll have to incorporate it over here. So it's a long-term process to get there. But this project is important because till date, Indian Army has been having something called as trolls or blows to excavate these mines in wartime. So these trolls, what they do is they have these just like your JCB. You put the entire machine under the ground and you pull out the soil itself. So when you pull out the soil, the mines they keep on blasting off. So the arm of that machine, it's a huge machine, much bigger than the JCB. The arm of that is made of such an alloy that it does not blast off with the mine, but it creates a lot of sound because the mines are blasting off. So when you are in a war and you know that you want to attack from this particular area, but it's creating a lot of noise, then the enemy will also know that you are attacking from this place, and they will start their counter attack on you. So they wanted a silent system which can just go around and mark up the things, and so that the enemy will never know from where you are attacking. That was the reason why it was taken up.
So the video looks like that this is going to be in production really soon.
Yeah. Next year we are getting into order.
Great. Thank you so much.
There is a air gap you mentioned, and then I was thinking, the machine is roughly 3 foot by 5 foot. Correct? It's still big if you see.
It's quite big.
It's quite big, right? Why is the size big? Is it because the size of the sensors inside is
Combined together, the size of the sensors, the area we had to cover is about 6 odd meters. So there are about 3 machines which would be deployed in parallel, each covering an area of 2 meters. So imagine a stretch of 1 kilometer long and 6 meters wide. About 20 odd feet you need to clear off. Possibly the distance from here to where Adarsh is standing. You want to clear this entire distance off. So what we have done is we have taken 3 such vehicles which work together. It's in a semi-autonomous form, and and that's why the vehicles are bigger in one way because of the distance you need to cover. Secondly is the terrain. The terrain is a semi-desert terrain which you require stable, sturdy vehicles to go there. So the vehicle sizing is also dependent on the terrain and the size of your wheels and other things from the physical characteristics perspective, and also the sensors. So everything combined together is the size of the vehicle.
such kind of a precision is still possible in a setup with a very accurate gyro like a drone, which could also.
So drones have a certain limitation. They are exploring drones as the next step, but they still have a certain limitation in all weather conditions. One, because if there is a lot of winds and stuff, it becomes difficult to control the drone. Secondly, as I said, the drones will follow at a certain distance from the ground, and the air coupling increases for the ground penetrating radar in such scenarios. So maintaining a drone exactly parallel to the ground with a certain air coupling, it's still under research. So there has been no active product as such in the market, but there are a few universities who are working on it right now. A couple of them in US and Europe. None of such active research happens in India. So even these two products, what we are working on, or what we have worked on, I mean, these are something like very niche, which is absolutely, you cannot fathom anyone working in India till date on such products. They're generally imported from US or Israel or Russia or France in some places. So yeah, drones are being explored, but the technology is still not mature enough to be deployed.
What's the next phase for Sync? This is one.
So,
what else?
So we keep on pursuing this. There are in fact, a lot of opportunities for us to become Indian OEMs for such products and compete with the foreign OEMs. Secondly, what happens in defense is very interesting because the demand comes from the end user. So we don't have to go ahead and create a market for it. So, the army will say, or the Air Force will say that these are the things what we want on the field. And then instead of going ahead and purchasing it from the outside, you go ahead and, make it happen for them. So we are a tech company. We combine electronics along with AI and GPUs and UI. So whatever kind of problems come up, that is something what we are excited to pursue on this in this particular domain. And even the Indian Army and the Air Force are happy because what happens when you have foreign-based OEMs is you don't get access to their data, you don't get access to the tech what they're working on. It's a complete black box which comes in, and there are certain kinds of data what they want. They want to customize certain outputs. They want to make sense out of data in some various other ways to form the strategies. But those things are not available. Secondly, what the foreign OEMs always sells you is at least 3 tiers of technology below than what they're using right now. So that is where India will always be chasing rather than pioneering in something. So government has initiated these, there's various under these various schemes and stuff that you guys participate and go ahead, and that's possibly a good boost for us. So that's something what we are looking forward. In terms of the business verticals, we are also looking into expanding into quantum over a period of time. The GPUs are definitely there, but what is happening now is if you are aware about the Moore's law, of the semiconductors and so on. These days, the transistors have gone so small that there's a gap of about, I guess what I read was about 11 atoms now. And you cannot go below 5 to 6 atoms. So now we are reaching a space where hardware improvement in transistors will eventually reach a bottleneck. And at that time, there would be a certain paradigm shift required in computing, which will come up. So very few companies in India in quantum, so that is what we are exploring. Although the current application areas are limited, specifically into cryptography and other quantum spaces, but that is absolutely essential in defense again. So we are trying to get some front-runner advantage in that. Secondly is free space optics. If you have heard about free space optics, it's a very new field which would be used in communication as an alternative to RF. So that is based on laser-based communication, and it's the best advantage of free space optics. It cannot be hacked. So that is something what we are exploring as well. A lot of IITs and other institutes are kind of researching on that. So these two are something which will eventually become practical, possibly 5 years or maybe in the next decade. So that is the eventual goal where we are moving towards. Thank you.
Amazing stuff. Really cool.
One more, I guess. Adarsh?
Hello.
What's the difference between Li-Fi and space?
Sorry?
Li-Fi.
Li-Fi.
Yeah, something like what we have Wi-Fi.
Sorry, I've not heard about Li-Fi.
It's a laser-based computing.
Okay, but free space, so yeah. Right, so it might be a different name for free space optics itself. I have not explored Wi-Fi much, but in free space optics, obviously, as it's a laser-based communication which works on huge distances. So you can have, say, for example, a ship in the middle of the ocean and command and sending waves to the control station back in laser-based communication, using satellites. So that is something which is pretty much that is there as an open challenge for the defense to get in. But Li-Fi I have not explored. So sorry, I could not answer that question. Yeah.
Actually, back to the technology, I really appreciate that what you have been developing so far. It's just there is a curiosity in my mind. So how you have solved false negative scenario here?
Okay, so false negatives are always a part of it, but what we have done is we have false negatives are still not that much of a it's still what you can say that we have conducted a couple of trials wherein as we fuse the data sensors output together, there might be false negatives coming up in okay, sorry. Yeah, so you might get false negatives in one of the sensors, and the other sensor might pick up the signal, what is important. So when we started off, the false negatives were definitely a problem. False positives, not a problem because it's quite okay that you get something. But still, statistically, it is important because you don't want the soldiers to dug out every possible false positive which is coming up. But false negatives is exactly the reason why we went for a data fusion approach, wherein you have multiple sensors. So if there is a false negative coming up in one of the sensors, then other sensors will pick up. So false negatives are a part and parcel of this what comes up. So the overall data accuracy improves when you kind of combine everything together and get it done. Yeah, I mean, like till now we have been good enough that we have been catching the anti-tank, anti-personnel mines and other fragmentation mines and so on. It's been quite good. And accuracy has been very good. Thank you.
Yeah. So you talked about quantum computing. What are your thoughts on future in India for quantum computing? Like it's been researched as of now.
It's quite research. I mean, like it's the kind of hardware what is being used on that is something where you still don't have that kind of hardware exposure in India. I mean, there is Google and other companies who have so they have the quantum computing lab over there, and you basically tie up with them and you explore their hardware at that time. So I don't know when this would be made available here in a way where you can actually use it in India, but I'm pretty sure that once there are a few companies, and it's more like a market decision that you find that there is a substantial business coming in to set up such a lab, and you have business opportunities coming up, then pretty much the government will take some initiative at that time. So it's still in its infancy, just like GPU was in infancy, possibly early 2000. So, but over the next 2 decades, it will definitely take off, and I'm pretty sure that there would be some good innovation from NVIDIA also coming up on that to see. So because they would not like to leave the bus at that time, they will come up with something. So let's see what happens.
Okay, nice. I think we'll take the questions afterwards. I think we have a post session where Rushabh will be available and you can ask all you want. Okay. Thank you so much, Rushabh, for this exciting so Rushabh has mentioned Jetson a lot, so I thought I'll just show you. This is how it looks like. Okay, it is that small. Okay, it has 128 cores. Okay, I am keeping it here, and you can also have a look, like hold it in your hand and see how like these guys are developing amazing products on this. Okay. Next, I would like to call Mr. Megh Makwana from NVIDIA. He is a solution architect and he's handling a team who is working on speech AI and conversational AI. And he will be present his talk to you. Please welcome Megh Makwana.
Okay. Hello everyone. Good evening. And I think there were a lot of good questions that came up today. Like, GPUs are coming every year. A lot of people are making it. But what really differentiates us is the software here, and people typically, forget that. So the key thing that I really want to talk about today is, specifically if you look today, generative AI as a technology has become so mainstream, and it has become so impactful in the sense that it's going to literally change the way we are using a lot of these applications today. And what I want to do today is I want to first give a little bit of an overview of how people are building it for English as a language. And some of the work that we have been doing in India is how do we sort of get these things to also work as effectively for Indian languages. So with that, maybe let me just give you a little bit of an overview. So if you look at building real-time conversational AI systems, it has everything right from you asking a question to the model understanding what has been asked to the and the output that gets generated from that LLM model possibly then getting sent to a text-to-speech system that converts that corresponding answer back into speech, and then you take that speech back and you sort of do something called as lift synchronization of what is being said on an avatar. So what you see here is that right from speech recognition, you're putting in your input speech, you have a large language model that will answer the thing that was asked after the speech recognition part, and then you have text to speech that will convert the answer back to a human-like speech, and then that will then get rendered on top of an avatar that will speak back to you, right? Probably giving you an answer. Now people can do this whole thing, people can do half part of it, that's absolutely fine. Now, again, if you look at what is it that we are doing as a company around this entire workflow, is the fact that we are just not building GPUs for you to use it and build your own ASR systems, text-to-speech systems, build your own anything. Obviously, if you are a foundational company that has expertise in building this from scratch, please go ahead and do it. That's where you think of us as a platform company. But if you think that, hey, you know what, I just want to go ahead and start building applications out of it. I don't want to build my own ASR system, right? I want to probably use something that probably NVIDIA has built or somebody has built in open source, and I want to use it highly, and I want to make sure that whatever I using is also robust enough. It's not like it's just very good on academic benchmarks, but it should actually work in real life problems, and that is what I'll be discussing today. So with that, let me first give you a little bit more overview on the aspect of how do these things how do these things look in production when we look at it from an English, from an US standpoint, where people generally want to build this everything in English. So probably this is just an example of a talking kiosk. Maybe the audio is a little low.
Hi, welcome to Shannon's Cafe. How can I help you?
Can I have a cheeseburger with a side of onion rings, please?
Would you be interested in our popular toppings for cheeseburger like bacon and fried onions?
Yeah, let's do it.
Done. Added cheeseburger with bacon and fried onions. What else?
What protein options do you have?
We have multiple options. I recommend the double protein burger. Would you like that?
Do you have any vegetarian options?
I can get you a black bean patty instead. Would you like that?
Sure.
Okay, I have added double protein burger with black bean patty to your cart. What else?
Do you have any sides?
We have these 3 vegetarian items. French fries, onion rings, and fried pickles. What would you like?
I'll have the French fries instead of the onion rings, please.
Sure. Would you like some garlic on it?
Yes, please.
Okay, I have added French fries with garlic to your cart. What else?
What salads do you offer?
We have market salad, Cobb salad, fruit salad, and side salad. Side salad is popular with our cheeseburger.
I'll do the side salad.
Alright, if it's sunny out there, would you like to add some drinks? I recommend our lemonade.
Sure. I'll have a cola.
We have 2 options, Diet Cola and regular cola. Which one would you like?
I'll take the latter, please.
Adding regular cola. Anything else?
That's it. Thank you.
Okay, your total bill is $24.46. Your food will be available shortly. Thank you.
Thank you.
Thank you. Bye.
So as you can see, again, a real-time system working that you can basically put it in some retail store, and you can actually start doing food ordering through this conversational AI system. And again, if you look at this, and then if you think that, hey, can I build something similar for Indian languages? How hard can the problem be? And why should somebody even build something similar for the Indian, for Indian languages? That might be a question that people might have. So let's probably just look at some statistics that will at least provide some view of why building. And again, see, I'm not talking about that only that application. I'm talking about building foundational technology for speech to text, text to speech, LLM models, as well as actually after zooming, the problem is that it goes on the other screen. That's the problem. Sorry about that. So if you actually see in India, obviously in the tier 1 cities, people are very comfortable with English, and obviously people are, even in tier 2 are learning English quite a bit. But if you see today, there is still a need of building these systems for Indian languages, because still a lot of our population in tier 2, tier 3 still prefer to speak in their own mother tongue. And there's a very large diversity that is there in the country. Now let's look at Hindi as an example, because if I start talking about all languages, it will become a much larger topic. Let's specifically talk about Hindi. And when we think about Hindi as a language, what is some of the problems that you possibly might think could be there from a speech to text angle? Right? Let's think about speech to text as the first modality, and then try to think what can be some of the challenges. Some of them I've listed down here, which are quite prominent. First is code switching. What is code switching? It means like जब भी मैं हिंदी में बात करता हूँ, but कभी भी I'll probably add a little bit of English inside. Now, point is, can your speech recognizers do that switching? Okay, that's a very important and an interesting research problem to solve. So, what we actually do at NVIDIA is like we work on these multidisciplinary problem statements on addressing some of these problems so that you as an organization who might not want to build these foundational models can actually take the things that we have built, because everything is open source. Go ahead and use it for your building your own end application. So let's look at code switching as one of the problem statements. The second could be multi-accent. That means, what happens if somebody who speaks Bhojpuri uses your Hindi speech recognizer? Does it still generalize well even on that Bhojpuri accent? That can be a problem statement too. The third problem statement is noise robustness. That means, like, imagine like I'm there in a boardroom and I, as a speaker, is trying to speak in front of the mic and I'm saying something. Now, there will always be a lot of background noise where people are probably shouting, yelling, right? How do we make sure that the speech recognizer focuses on a single user while he is trying to give his speech, even in noisy environments? And the fourth is real-time streaming. What does real-time streaming mean? So, typically in speech-to-text systems, there are two ways of running inference on top of your data. One is you already have a WAV file, which is an audio file sitting on your computer, and you take that entire WAV file and then you process it. That means you transcribe whatever has been said in that audio file. That's one way. Second is that I want to do this transcription in real time as I speak. That means I have a microphone and the transcriptions are getting generated in real time. That is called as real-time streaming inference. So again, these two type of inference are two different problems, and doing it in real time brings its own set of challenges. So now let's look at some of these things in action, like what kind of things can be done. So before that, maybe let me just give you a little more detail of how speech-to-text systems work. So if you see, when you take your raw audio file, okay, so there's probably speech signals that is coming in. This speech signal goes inside something called as a feature extractor. This feature extractor will essentially take this raw audio and will convert that into something called as MEL spectrograms. Once it's converted to MEL spectrograms, it goes to an acoustic model. The task of the acoustic model is to take these raw MEL spectrograms and map that to some transcript or to some word or sub-word. Right? So, say for example, if I say hello, it will basically in the model of the output of the model will be HELLO. So the model is outputting 6 characters. Now, with the advancement in these algorithms, instead of predicting each character, we are now predicting something called a subword of tokens. That means say HE will be one token, L will be one token, LO might be another token. So instead of doing 6 times generation, you have finished that generation in only 3 tokens. Because now instead of doing character wise, you're doing it on subwords. And that is why I'm sure if you have read some news about that ChatGPT takes a lot of needs a lot of generation steps to generate Hindi output compared to English. This is for that very specific reason, because you're doing character wise and you're not doing subword wise. Okay, so you basically have this acoustic model that takes that MEL spectrogram and maps that to some textual output in form of subwords or even in form of characters. Both are usable form. But the problem with this is that the acoustic model, whatever it is giving as an output, does not have a sense of how language is structured. So you need another model that can sort of help you to do rescoring in terms of how the language is structured. So you have a very small language model called as KenLM, and you use that for rescoring the transcripts from the acoustic model so that it makes sure that whatever is being said makes sense grammatically. Okay. So you have this small KenLM over here. After you do that, you also need something called as punctuation and capitalization for the text to look readable. Okay, so we have like a bird-based encoder model doing punctuation and capitalization. And then you have something called as inverse text normalization. What this means is, when I say मेरे account से मेरे भाई के account में 500 रुपए transfer कर दो, 500 will be written in the Hindi form. Okay, it's in form of words. But typically, when people want to do some downstream NLP task on top of this, they would want those so as word form be converted into 200 as a numerical format. That's why you have your inverse text normalization. So this is how it works. Now let me talk a little bit about how can you think about customizing these different blocks based on the issues that you see after you have trained the model. Okay, so the first thing is that you can do something called as word boosting. Now what happens is, now let's say I say something called as geo. Okay, I'm using a speech recognizer from say some company and I say geo. Now what is geo? Does it mean GEO or does it mean GIO? Now if I am somebody like Reliance, I would want to put more emphasis on GIO, right? Because that is what it means for my particular lingo. So you do something called as word boosting, where you're boosting the probability of specific words during runtime. Okay, so that's the word boosting part. That's on the customizability part during inference. The second is, if your acoustic model is not able to pick up accents, that means, say for example, you train this model on some data set, say with XYZ language, say for example, speakers from say Maharashtra, somebody from Rajasthan, but then now you take this ASR and then you run it with somebody from say Northeast, and you might see that the model is not generating correct outputs. That means your model is not generalizing to that accent. That's where your next step would be to retrain this acoustic model. Okay. Now the third is the language model. When do you do language model retraining? You do that when your important vocabulary words of your domain are not being properly emitted from the model. Okay. That's why. So again, anything that is domain specific and lingo, you retrain your language model, not the acoustic model. You do acoustic model retraining only when there is a transfer in accent. Then you have your punctuation and capitalization. This is pretty straightforward. I won't touch much on that. And then you have IT. Now let's look at some, how have we sort of tried to solve these problems. So the first problem I'll show you is a Bhojpuri speaker and a Hindi speech recognizer. How well does it generalize?
ऐसा गायक लोग से भोजपुरी के बहुत नुकसान हो ऐसा गीत से कहीं बाकी या भोजपुरी के बचाएं एगो आईपीएस अफसर बड़े मृत्युंजय वहाँ के भोजपुरी में उपन्यास लिखे बने गंगा रतन विदेश तो भोजपुरी में लिखाई पढ़ाई हो बिहार विदेशिया हो लेकिन चोली लिपस्टिक वाला गाना पर विचार कर लिया हमने के भाषा में बहुत कुछ बा कजरी देखत नहीं कि हमारा मकसद पूरा मकसद गाय कजरी ब्रेकली एक्चुअली मातृभाषा पर आप सभी को बधाई, चाहे आप बांग्ला बोल रहे हो, तमिल बोल रहे हो, तेलुगु बोल रहे हो, या अंग्रेजी या स्पेनिश या फिर उर्दू या फिर मराठी या फिर गुजराती.
So, as you could see, it was generalizing pretty well on the Bhojpuri accent as well. Let's look at the other problem statement, which is of handling background noise, and then I'll also show you code switching as well. And I'll show that in real time so that it feels that it's just not recorded.
सम्मानीय सदस्यों से मेरा आग्रह है कि एक बहुत संवेदनशील मुद्दे पर काफी सदस्यों ने सत्ताधारी दल के और विपक्ष दोनों के सदस्य ने चर्चा की मांग की है. मैं सदन में चर्चा के लिए तैयार हूँ. मुझे मालूम नहीं है कि विपक्ष की चर्चा करने देना नहीं चाहता. मेरा विपक्ष के नेता को आग्रह है कि चर्चा होने दें और इस महत्वपूर्ण मसले पर पूरे देश के सामने सच्चाई जाए. बहुत महत्वपूर्ण.
I think the message is clear, but let me show you the code switching part in right away. Right? So this is the UI, and I'm gonna go towards Hindi, and again I'm using my mobile internet. So again, even if you say deploy this on a mobile phone device, it's gonna work well because I'm using mobile's data to transmit this up. जैसे कि आप देख सकते हो ये स्पीच रिकग्निशन सिस्टम इवन इफ आई स्पीक इन इंग्लिश और इवन इफ आई स्पीक इन हिंदी इट इज एबल टू ट्रांसक्राइब इट बहुत इफेक्टिव. So as you can see, it is able to capture English as well as it's able to capture Hindi, right? And so again, we have tried addressing all those three problems, and what we keep telling to all our partners, because everybody who builds on our platform is like a partner to us. We say that, hey, listen, if you don't want to if you want to start building your products, you want to have these capabilities, we have made all of these models open source. Go ahead, use it, the platform is there. You can go ahead and start building your platform and adding these services directly on top of it. So you don't have to do the research in terms of building it from scratch. We are doing it for you because our goal is to build platforms so that the community can build on top of it. And again, these are like really tough research problems that me and my team basically focus on working and trying to make it more generalizable. Now, I'll probably move to the next part, which is text to speech. Probably before that, let's look at another application. Like, say, for example, I want to now not just do speech to text, but I want to do speech to text plus translation in real time. How do I do that?
When it comes to education and healthcare sector compared to all other states in India. Unlike other parts of India, Kerala is progressing rapidly with an active state government, literate citizens, and modern infrastructure. Kerala is quite ahead of its time. It is also noteworthy that Kerala has the lowest infant mortality rate, the lowest maternal mortality rate, and the highest female to male literacy rate in the country.
Yeah, so as you could see, we are now able to now combine speech recognition along with translation to build speech to text translation systems in almost real time. So this is another application. Now let's move to the next part, which is text to speech. Now what is text to speech? Text to speech basically means that I'm putting in some text and then the model is supposed to generate speech or audio from that text. And typically for doing this, there are two sides of the model. The first one is called as a Megh spectrogram generator, and the second one is called as a vocoder that takes the Megh spectrogram and converts that into the audio. So you pass in some text, you do some text normalization and pre-processing. Why do you need to do that? If you type something like, hello, my name is Megh and my age is 27, now the 27, which is in a numerical format, needs to be converted to words. That's why you need text normalization to convert that. After you do the text normalization, you tokenize the text into text encoding. After you take the text encoding, you also have the ability to do inference time modulation of your speech in terms of pitch, in terms of duration. And also, we are working on something where we can make a speaker speak multiple languages without having his data in all that language. So additionally, you can also have control over accent and language that the system is trying to generate. But here I've just kept pitch and duration as an example. And then you use those predictor attributes. You send it to the spectrogram generation model, typically models like fast pitch or RAT-TTS. Those will generate the spectrograms, and then those spectrograms are sent to a vocoder model, typically models like Hi-Fi GAN and others. And then you get the corresponding output audio. Now, you might ask a question, hey, what modifications can I do to an existing text-to-speech system? One modification that you can think about is, say, for example, you're working with a brand, and now the brand wants to build, say, a conversational AI platform for their mascot. Say their mascot, as an example, say Amitabh Bachchan. The company needs to sort of, say, for example, work with Amitabh Bachchan, ask him whether it's fine to take 30 minutes of his audio file, and then you can basically create Amitabh Bachchan's text-to-speech systems directly for that specific branding. Again, this is just an example. There can be different ways in which people do this, but the thing is that you can now, even with just 30 minutes of studio quality recorded audio of your mascot, you can now transfer the voice and generate really good voices. And that's where the fine-tuning part basically comes in. I'm not going to a lot of details just in the interest of time, but if there are any more questions that you have, please feel free to ask those questions after the session. The next part is large language models. Now, again, large language models in general have taken up a lot of momentum in the entire community. And this is largely because it's actually solving a lot of problems and increasing the productivity of humans. Some people have this thought that, hey, LLMs are meant to replace people. The answer to that question is no. It's not meant to replace. It's meant to actually augment and make your work faster. To give you an example, if somebody were to say, say as an engineer, right, I'll sit probably, I'll write some code. I'll probably go on, Stack Overflow, look for some answers. Everybody does that. Now, instead of that, can I now talk to an AI system that can help me generate code for a specific task, and then I can just modify it based on my requirement. Now, what is it doing? It's basically helping me out. Previously, also I was going on Stack Overflow, but I did not have an interacting system where I could like ask some more follow-up questions on top of it. So the thing is that instead of going on Stack Overflow, putting some queries and then waiting for somebody to answer back, you can have an AI system that is sort of helping you as an assistant to do your coding work faster, and nothing wrong in it, right? So that's where, again, this is one example of text, code generation. You can, but apply this to a lot of other fields. Like pharma is a great area where people are trying to use LLMs for doing drug discovery. Now, again, I'm not an expert to talk on it. I think Gaurav of the team does a much better job in explaining that. But there's a lot of areas where LLMs are becoming extremely useful. And my only 2 cents is that, do not, think that, hey, running LLMs is hard or it's expensive. But please have a thought process that, hey, how am I going to use this to make some of my existing workflows more efficient and make my workforce more productive using this tech? Because see, this is coming, okay? There is no stoppage to it, right? People are going to start adopting it. Sooner or later, you will realize that, hey, I should have gotten onto the bus much before this, right? So, okay, just a school of thought. But let me talk a little bit more on details around it. So, see, LLM is a very vast topic. Like we can spend hours and hours talking about it. But what I thought today is I want to address one of the important problem statement that everybody makes as a statement. And sometimes, I've also seen it's very funny. People just read it on the internet and they say that, hey, you know what, running LLMs is very expensive. GPUs are very expensive. Again, see, that's not true. Okay, and that is where I thought that I'll try to address one of this key concern that, hey, how can you make your LLM run more effectively on the underlying hardware? And again, the answer to that question is again software. Okay, it's just not the hardware. It's actually the software stack that makes the hardware really give you the bang for your buck. So this is just 2 days back. Okay, we've released a new compiler technology called as TensorRT LLM. We already had TensorRT. Just for you guys, just for you folks who don't know what TensorRT is basically a compiler technology that is used for taking these neural networks. Now, what are neural networks? Neural networks are nothing but these are graphs, and you're flowing in some tensor information in terms of large matrices across this control flow of the graph, and you're doing some operations on top of it. The deep learning compiler, which is TensorRT, essentially will take these graphs and will apply fusions on top of it. So you can think of that, hey, if I'm taking a CNN model, just as a very simple example, I have convolution, I have patch down, I have render. Now, do I execute 3 CUDA kernels for it, or should I fuse all of these as one single CUDA kernel and reduce my launch from 3 kernels to 1 kernel? Okay, so it's going to do those kind of graph-based optimization across the entire neural network graph. Second thing it does is that it allows you to reduce the precision. Now, typically for training models, BF16, FP16, and FP32 is what was the standard. But for inference, you can now go all the way to IN4. And again, I'll talk more about the benchmarking details as well. So with TensorRT, you can take these models, do graph optimizations, and make it into a highly optimized format, and also reduce precision so that you can get much better latency and throughput. And again, it has a lot of these really interesting features. If somebody wants to talk more details around it, I'll be happy to talk about it after the session, but I don't want to talk about all of it just right here. But these are some of the key capabilities that we've added, like KV caching, custom multi-head attention fusion blocks, in-flight batching page attention, multi-GPU support, and so forth. This is how it looks like from a software angle. So on the topmost side, you have your frameworks. Again, framework can be PyTorch, TensorFlow, or you might be using some other frameworks like Pattern, JAX. You take these models from these workflows, and then you lower it down on the model building stage. Now, what happens over here is that there are certain, so in TensorRT LLM, you'll have to write how these models are, what the definition of the model. We have done it for some of the highly used open source models like Llama, some of the GPT models, MPT, all those GPT variants that you can find. All those are basically pre-built, and the model definitions are given here as to what has to be done in terms of fusion. Then we also have things like custom Tensor RT LLM package. This is for those people who write low-level CUDA code. Okay, till here, this is the developer layer. Do not go beyond this. As a developer, you just need to look into that. Hey, I have a model in this framework, and I want to basically build it. Do we have these purpose-built models through which I can compile these models? The developer stands here. But for those CUDA ninjas who feel that, hey, I know CUDA pretty well, and I have my own model architecture. Okay, I've added some new uniqueness to this, and NVIDIA does not provide a kernel. There is a flexibility for you to write your own CUDA kernels in this particular tool. So all these are layers written by the NVIDIA team to make sure that you get maximum performance. But if you feel that, hey, I want to customize it for my own modified version of the transformer model, you can bring those customizations over here. And then you basically have the runtime out here. Now let's talk a little bit about numbers, because that's what everybody cares about at the end of the day, right? Nobody cares, hey, I don't want to write those layers, just give me things that work out of the box. So here what we have done is we have given some numbers. So this is GPT-J model. Again, pretty standard, people are using it. Llama 2 models, and you can see that going from the A100 GPU all the way to H100 along with TRT LLM, you see almost 4.6x improvement in inference performance. Now that reduces your total cost of ownership of hosting these models as well. So a lot of time people also do this, right? They just take these models from these, PyTorch and other ecosystem. They don't do any optimizations on top of it, and they say that, hey, I'm not getting performance, GPUs are costly. But when you do this, this is when you start realizing that, hey, maybe what, this is how you can save cost, and it's not that expensive. One more important point is that the use of a little more lower precision, like FP8. So with the new GPU architecture, what we've really done in terms of the innovation is that we've added this new precision format that supports the underlying tensor cores is the FP8 precision. And we have realized that, hey, you don't always need FP16 and FP32 to keep the accuracies intact of these nodes. You can use also something like FP8 and keep the accuracies at the same level. Now, this using of lower precision results in a lot of using these low precisions actually help you to host these large models on less amount of GPU memory, because instead of FP16 you're now hosting it on FP8. So if your previously your model was 80 GB, now with FP8 you close it down to about 40 GB, right? So there's a lot of memory savings as well, and because of the FP8 tensor cores within the Hopper architecture, the inference performance is also much higher. So again, that's another thing to keep in mind over here. So again, it's an open source platform. If you're using LLMs, you're deploying it on your own, please go ahead and try this, see how much performant it is, and you will see that at the end of the day, it's not that expensive. Again, these are some baseline numbers over a baseline framework. Again, can be PyTorch, I'm not going to name them. Versus using it with TRT LM. You can see that even for something like Llama 70B, the improvement is almost 9x. Okay. Again, massive improvements. So again, my 2 cents is that, hey, if you're using LLMs, start using all of this open source stack and then see how much you're able to do cost reduction. In the last part, probably I just showed you an end-to-end voice bot that we're currently building and expanding upon, where we have added Hindi ASR, Hindi LLM, and a Hindi TDS model combined together.
भारत के प्रधानमंत्री कौन है?
भारत के वर्तमान प्रधानमंत्री नरेंद्र मोदी वह 2014 मई से प्रधानमंत्री।
जेनसेन हुआंग कौन है?
जिनसन हुआंग मीडिया के संस्थापक हैं जो एक बहुराष्ट्रीय निगम है जो कि आर्टिफिशियल इंटेलिजेंस और ऑटोमोटिव सहित विभिन्न अनुप्रयोगों के ग्राफिक्स प्रोसेसिंग इकाइयों और अन्य हार्डवेयर को डिजाइन करता है।
Again, it can be quite wrong, but I think people get the message. I think I'll spend the next 5 minutes just in terms of the time limit. If there are any questions, feel free to ask.
Hey, this is great and awesome. I have a question. So this may be Megh. So you are combining a lot of tools here, right? Are you using framework kind of LangChain or Llama Index here?
No. So again, that's a good point, and I know why Llama Index and LangChain typically comes up. And what we say is those are great to get started, but is it production ready in terms of is it really distributing your computing effectively? Are you running your embedding models effectively? All of that is running in Python. It's not effective. So what you do is we are working on an open source repository where we'll be taking the Llama Index framework, where you have the embedding model, you have the vector database, and then you have an LLM, and we are going to basically take them from the Python runtime to this TensorRT and Triton runtime. What will happen is the embedding model again is a neural network. You can use TensorRT to graph optimization on top and make the performance much better. Just primarily, some numbers that I can share is we have almost seen 5x better throughput moving from the LangChain inference of these embedding models on then using it on TensorRT along with Triton. The second part of this is vector database. So people typically use Fias and Winverse. We have something called as Raft, which is our own very high-speed implementation of these vector algorithms, and that is now also made open source. So what I would suggest is that prototype with LangChain, Llama Index, great ecosystem. But if you're looking at more performance, put them on top of these compilers and then deploy it because it's going to be more effective.
Thank you. And this is a follow-up question. So you mentioned about RAP, right, vector database. So how does it compare with other vector databases like VB8 or Phase, whatever you mentioned? So how does it compare with other vector databases?
The simplest thing I would say is that people have been building it on their own. We have built them in a way that we know that hey, this is the most optimized way of building it, and then we have made it open source. I wouldn't exactly compare it with other ecosystem players because everybody are building it based on their expertise. But if you're looking at performance, you should also explore Raft and then make a decision that hey, across these 4 open source vector databases, what ends up being the most performant. But it's very similar. It's just that the implementation and the algorithmic kernels that gets used would be different, but logically it's still a vector database. It's very similar.
Thank you.
What kind of a backend is this using right now? What kind of a GPU is this using?
So this is currently using A100s, but does not necessarily mean you have to deploy on A100s. So we also have certain GPUs that are meant for inferencing, like L4s, L40s, which will give you much better price to performance ratio when you are trying to deploy such systems. So right now it's on A100 because that's what we had internally and that's what we ended up using. But you can also use other GPUs that might give you much better price to performance ratio, like L4s, L40s.
And any idea about how many tokens per second would this be emitting?
So basically here we are doing approximately, so again, this is streaming use case. So in case of a streaming use case, it will just be real time. So it would be approximately 1 token every 0.01 second. But again, if you increase the load, that means if you increase the number of concurrent users, the latency will increase from 0.01, it might increase all the way to 0.1 or 0.2 for the first token to get generated. So again, it depends on how many concurrent users are there on that GPU. If it is a single user, your latency will be the lowest. But if your batch size is going from 1 to all the way to 128 requests coming in, then your latency might go for the same model on the same GPU from say 0.01 to 0.2 or 0.3 as well.
Thanks.
Hi, Megh. Great presentation. Thank you so much. I just wanted to understand the architecture over here, like what all models are being used here in this whole pipeline.
Got it. So basically here we are using three models, actually four models. The first is the Hindi speech to text model. The second model here we are basically using a translation model for the intermediate generation. This is not an Indic LLM model. Okay, this is still an English LLM Llama 2 model that we are using, and we have added translation systems after the speech to text. And so you have ASR, which is doing the Hindi text output. And then you have a translation model that will convert that from Hindi to English. The English will go as an input to the English LLM, which is Llama 2. The output generated from Llama 2 will then again go to a translation model, convert that into Hindi, and then it will be sent to text-to-speech models. In terms of the model architecture that we have used, for ASR it is conformer. For translation it is Indic Trans 2 based on the encoder-decoder model, which is again a transformer, encoder-decoder. And then you have Llama is again a GPT based decoder, and then for text to speech we are using RAG-KTS and Hi-Fi.
All of these models would be open source.
Everything is open source.
Great, thanks.
So all of this is hosted on one 800 or different 800?
So the LLM is a 70 billion model, so it needs at least one A100. The rest ASR and TTX is running on a single GPU.
Okay.
So total GPUs.
Okay. Any other questions?
Hi. So the transcript generator you showed, does it support the multiple channels? Like if there are multiple speakers in the audio, so does it do the channel separation, or do we need a special type of audio input for that?
That's a very good question. So we don't do channel separation. In order to do transcription for multiple users, you consider all of them as a concurrent user on top and sending that as a request. So we don't do channel separation at this point. We only give the channel of the speaker. In this case, probably was the YouTube video, and all the noise that came in was flowing in the single channel. But if you have multiple speakers, you will have multiple channels. But it cannot be like one channel, everybody are speaking, and then you're separating the transcript of every user, because then you need to do diarization. So that's a different problem state. So we are not doing diarization.
Right. Okay. My follow-up question is: if once the transcript is generated, do we have some sort of customization available, so that let's say if I want to do PII redaction, right? So do we have to add customized layer at the end of it, or does it provide some sort of inbuilt fine-tuning that it does the PI redaction?
No, it does not do PI redaction, because that's a very good question again, because we get this a lot. We'll have to build an additional layer, downstream layer on top of it. People typically tend to use BERT. They do things like masking, specifically for like people name, addresses, some important information like you said. Use BERT models, do masking. I mean, that is one of the way, not the best way. People also use the models like BART to also do it. Again, there are different ways to do it. But no, it does not have it in the acoustic model. You will not have PII reduction in the acoustic model. It has to be downstream and in the upstream.
Okay. Thank you.
Hi, I'm Deepak. I just have to understand from you that do the emotions also get captured when you do speech to text?
Not during speech to text, but we can do that in text to speech, for which I think I forgot showing that demo. Like for doing text to speech, you can emulate happy emotion, you can emulate sad emotion, you can emulate neutral emotion. I'll just show that a little bit, but not for speech to text. No. There is no emotion recognition.
So in India, there are a lot of vernacular languages, right? So, and within that, there are also subcategories. So if you need to train the system, so what's the solution to that?
You add all those. So say for example, it's say Bengali. Bengali has say 5 subdialects.
Correct.
You add all of that together and build one model. You don't build 5 models for different dialects, because you already have very less corpus for each of these dialects. It's much better you train one model, you train it with all these different dialects so that it's more robust. That's what we did in the case of Hindi. But one thing you can do is you can have your KenLM model, which is the decoding model, that can be a different KenLM for every dialect. So the acoustic prediction, the greedy scores that you're going to get from the acoustic model, you can send based on the dialect, you can send that to that nth KNLM model for which you have trained the text model. So the KNLM model is the text model. Then you can do dialect level decoding, because the grammar of a specific dialect might be different than the other dialect, but not the acoustic sound of it. So for acoustic model, let it be trained on all dialects, but for downstream KNLM decoding, you can have different KNLMs. Or you can also have one, but you can also choose to do multiple.
So while you'll be training it, is there any specific parameter that this amount of data, this GB of data, or these number of parameters needs to be fed?
Actually, there are no golden rules to it, to be very honest. Like I've learned over the past couple of years, one thing is it's all experimental. Okay, you cannot have a golden rule saying that, hey, I'm going to get 2,000 hours of data and I'm going to build the best speech recognition. Answer to that question is no. I've seen also scenarios where people, even with less data, have built a more robust model just because they knew how to iterate over the errors and then fix it back. Again, these can be in terms of training a much better KNLM on a specific area that the speech is coming from. So I would say that there's no thumb rule, but if I had to give you an answer of how much hours was needed to train this Hindi model, we used approximately 4,000 to 6,000 hours of Hindi corpus to train this. But my take is that to build really good models for your use case, for your domain, please do an iterative study. Find out where the errors are coming from, and then try to go back and try addressing it rather than finding a golden rule for it.
And how is this particular application different from IBM Watson?
See, it's hard to say because I don't know what they use within Watson, but I'm sure it will still use tech. Like they will use some speech-to-text model. In our case, we're using a conformer model, which is a mixture of transformer and convolution. It was actually published by Google back in 2018. What IBM uses, I'm not sure, but I'm sure they're using some acoustic model, and they would have probably used a neural-based model only. A conformer is one.
Not maybe from the architectural point of view, but from the applications, apples to apples comparison. From that point of view, I just wanted to understand. Obviously, the internal would be differently with IBM, but you haven't done any apples to apples comparison of your applications with any other competitive products in the market?
So see, we do that internally, but one thing is we don't share things externally because we feel that everybody is our partner. Everybody are in some or the other way using our infrastructure. So why build platforms and compete? So we don't believe in having competitive numbers to other players. Everybody is building their own stack. Please choose the stack based on what your need is. Somebody might prefer a specific stack because probably they prefer being on that cloud environment, and there's nothing wrong in it. So I don't have we don't publish external comparisons. What we say is that hey, you have your application. This is all open source. Compare it, see whatever works best, and then use it. But I don't have comparisons.
Thank you.
Any other questions?
So my question would be, the heart of this product tool is like the kind of LLMs we are using. So and most of the LLMs are kind of context limited as of now. So this TensorRT, first question would be for this TensorRT's context window. And if it is limited, how are we solving the information retrieval part of it, like sending the right context to the model and then inference part?
I think that's a very good question, a very good research and engineering question, I would say. So let's first address the first part. Context window. Can TensorRT solve your context window problem? Answer to that question is no. Because TensorRT is not changing the way the algorithm is working. In a sense that the context window is fixed by the tokenizer that you have trained. Okay, so if you might be using ROPE, you might be using Alibi. Now there are ways to extend that to a much larger context window. Now, when you increase the context window, what happens? You're basically increasing your memory footprint. Now, in order to address the memory footprint, what is the next problem that you'll have to think about? For that, you'll have to look at how do you make your attention. So the biggest problem with transformer is that the attention takes quadratic memory when it comes to the sequence length. And that is why we are stuck at 2K, 4K. There are very smart methods to extend that from 2K, 4K all the way till 16K or even beyond that. People like Anthropic have a context length of 128. So that is an algorithmic innovation on the attention mechanism, because the attention is the bottleneck here, not your compiler tech. Because the compiler is doing the graph optimization and doing lower precision. It's not changing how your attention works in the model, correct? So answer to that question is TensorRT will not solve it, but you need to look at some ways of doing a more efficient local attention based methods, and you can incorporate that in the model. There are ways to do it. I can share some more details because we internally are also trying to expand these models from 4K to 16K without exploding the memory while training these models. So there are ways to do it, but TensorRT is not the answer. Sorry, what was the second question?
Information driven part.
Very good. That's a very good engineering question. Now for that, typically there are a couple of ways to look into it. The first is you have an embedding model. So what you do is you take a large text document, multiple documents that you have as an information source, break that down into chunks. Again, this is the starting point and a naive way of doing it. I'll give you some more pointers on how to improve it. So you take a lot of these text documents, create chunk size of 128, 256, 512. Using an embedding model like say E5, might use PGE because that's the current state of the art, PGE and other models. Then you take these vector embeddings of these chunks, save it in a vector database, and then when you send a question, that question also gets embedded as an embedding from this model. And then you do a vector search and try to do a cosine similarity between all the vectors that are, all the chunks that are stored as vectors, embedding vectors in the vector stream. You do a cosine similarity and you try to find that, hey, which are the top 10 most nearest vectors in my vector database. And then you retrieve, say, 5 of them. Then you take those 5 chunks, provide that as a contextual information to the LLM saying that, hey, this is my prior knowledge of context. This is, so you convert that embedding back to text, append it as a text in your prompt, and then you'll ask a question saying that, hey, now answer this particular question. This is one way to do it, which is the most naive way, where LangChain and LaMindex help you to do it. Now, few things I just want to share as a personal experience of how you can improve the retrieval part. Here, you don't need to improve LLM, you need to improve the retrieval. You can start adding metadata to your chunks. This is something that I've learned over a period of time, that just chunking it naively is not a good thing. Because there can be scenarios where a paragraph is further chunked, the paragraph was very big, it's further chunked, half context got lost in this part, half context got lost here. You're not going to get a good retrieval system in that case. So I would say that adding metadata also sometimes has helped us internally while doing retrieval, while improving the IR system. Again, these are some of it. There are still better.
So we follow that thing. So basically we do parent-child chunking. So like send the parent chunk as well for every document, create a summary. So like while sending this chunk, send its parent, send one chunk above, send one chunk below, as well for summary of this one. So our experience has been, like the sending the summary is the most relevant, especially if the documents are very long, right? Anything above 100 pages. So, sending one chunk does not help at all. In fact, it confuses more because in the long document, the overall context is something else, and this specialized, this localized context is something else. So of all these, would you say that should we have the metadata at each, chunk level as well, or should at the document level? One thing, and second thing, like should we structure the document as well? Like if you have a code judgment, right? So like code judgment would have, one reason, assertion, conclusion, right? That kind of a structure, does that help as well? Or, if you have a obligation that is structured in itself, like abstract, method, your research, experiment, and then conclusion. Right? So does that help? Like should we chunk by these instead of fixed length by the part of the document? Right?
Again, I think that's a very good question as well. But as I would say, I might not have the best answer because it depends. Again, you might know better because you're working on the data. You might be able to iterate and find a better solution to it. So again, going back to what I said earlier, it's a experimental game. You'll have to try it. One solution that worked for me might work, might not work. So again, it's hard for me to give any recommendation because I would not know whether it will really work or not. But yes, appending metadata helped in our case. But for your specific case, I would say you just have to experiment here. I don't have a golden answer. There's no golden rule to fix those problems. It's all experimental.
You said cosine similarity helps in the information retrieval or the matching of documents. Is there any other way you tried or any other method that worked very nicely apart from this cosine similarity?
See, we are working on few things, but again, because it's not fully done, we have not done it comprehensively. I might not be able to give an answer even today. But we can probably chat about this a little later once we have more findings. But yes, there are better ways to also do that. Cosine is just one way, but there are better ways to do it, like having dual encoders and stuff like that. But I don't want to make any comment on the time. I don't have more data backing up it.
So I have a question on making of embeddings. So if my data is tables or let's say images, charts, so how can we handle that part?
Yeah, again, very good question. See, one thing we have realized, and again, like I said, right, see, it's a growing field. Everybody is sort of figuring out best ways to do it. What we have realized is, in case of such scenarios where you're dealing with tables, sometimes embeddings are not going to help you out. A better way to probably look at that problem statement is to probably use a vision model on top of it. Again, GPT-4 is the easiest answer that I can give you, but you can build such systems that can understand stable better. Retrieval might not be a very good way of solving tables, is what I feel. I could be wrong, but that's what we have seen internally. And hence, we are also scoping out of building vision-based transformer models for doing this, because that will have a better QA capability than converting tables into embeddings and then feeding it with real. Again, preliminary thoughts that I'm telling you, we are also researching. Once we have some more concrete thoughts after we generalize it, we can share it. But again, I think all those 3 4 questions on the retrieval part are very interesting research directions, and would love to talk about.
So for this information retrieval, would you suggest graph database instead of vector database, kind of, or you guys trying anything kind of?
We have seen people trying it. We are not doing it internally, but we have seen people use knowledge base and use graph databases as well. But again, I don't have experience because we have not used it in our project, so I might not be a good person to answer that question. But people are trying it, yeah, and people see the potential of it because you can now convert some of your knowledge bases into knowledge graphs, and sometimes retrieving answers from graphs is more easier than these vector stores because sometimes your IR systems are not really retrieving the right stuff. So yeah, it's a good area to look into for sure.
Thank you.
Okay, so we have 2 more sessions. So do you want a biological break? Okay, so we can start the next session in next 5 minutes. Okay, and then yeah, we have arranged high tea for you guys, but because of the our sessions took a bit more time than expected. But because you guys were interacting, I thought it's not right to stop you guys. So we'll have a 5 minute break, and then we'll start the session on introduction to GPU computing. Okay, so we'll meet back. We'll meet in 5 minutes. Thank you. Okay, so I've been working in GPU computing since last 10 to 12 years, and I've consulted a few of our customers. One very basic question came in that we have put the GPUs in the system, but we are still not getting the performance. The major reason behind that is they did not offload anything on the GPU. They just expected that if you put the GPU in the system, you're going to get the performance out of it. One of them is also are in the government, right? Even government thinks that if you just put the GPUs, you should get the performance, and that is the doubt that we are trying to clear here. As to we all talk about GPUs that it gives performance, it is used in AI, LLM, and so on, but we hardly talk about what it contains. Okay, so this session is basically to tell you that what are the components, what is a GPU, how does it look like, and just to answer some very basic questions. You might already know some of them, but it's good to have a look. So this is how a GPU looks like. For people who have not seen it, I have shown it the very basic version of the GPU. That is the ARM-based GPU. This is Jetson. This has 128 cores. The GPU that you are seeing here has 5,000 around cores. Okay, so like your laptops or mobiles that you're using, you have 4-core, 8-core, 12-core machines, but the GPUs talks in thousands. Okay, we have currently the GPUs which are coming up with 16,000 cores also. Okay, so GPU is an acronym for graphics processing unit. As Rushabh mentioned that back in they launched in 1999. Imagine that time. The screen resolution was somewhere around just for the simple calculations 500 cross 300. That's give you 1.5 lakh pixels of computation. Okay, so there was a need of architecture which was solely dedicated for this kind of computation, where they realized basically that you have same kind of data, you have same kind of instructions, but the outcome was different. Okay, I'm talking about the rendering part of it. Okay, every pixel has a different value, input value and the output value, but the operation that you do on a pixel to generate a frame is basically exactly the same. Okay, so we needed an architecture so that this kind of computation could be offloaded and the CPU computation could be used properly. Okay, so the application can become faster. You separated the rendering and the computation on different hardwares. So the major vendors of GPUs are NVIDIA, of course, and AMD. AMD hardly has any market share. GPU is an external peripheral. Most of your laptops are already working without it. If you don't put it, it's not going to change anything. It requires external power that ranges. There are some GPUs which does not even require any power, but it basically the power ranges from 30 watt to 300 watt. GPU is a term for GPU computing. Now, because it was it started with graphical for offloading the graphical overloaded, and now it is used for general purpose computing. So it's GPU. Major component of concern are basically two. One is the memory that it has, and second is the number of cores that it has. So we have Volta V100 with us. So it has 32 GB of memory and 5,120 cores. Okay. So CUDA is Compute Unified Device Architecture. It is the GPU computing language by NVIDIA for NVIDIA cards. It is free but not open source. We have three grades of GPUs: consumer grade that we see in our laptops. Okay, the GTX series. We have Quattro series, which is workstation grade. That is basically used for you can say CAD/CAM modeling and simulations, usually for the display purposes. We have data center grade like the DGX one that we have. It is Tesla grade, and it is basically for used for computations, where computations can be done 24/7, 365 days. Okay, so we have different GPU architecture code names like Fermi, Kepler, Maxwell, Pascal, Volta. That the one we are using, MPL, Hopper. Hopper is being the newest one. Okay, so this is the very basic information that you require to for around GPUs. Okay. Now, as we discussed, there are 5,000 or cores in 1,000 on a particular on this card. So they are not just put on a die like that. There is a certain fashion that they are put, and that fashion is called as GPU architecture. Okay. So they take a certain amount of cores according to the architecture that we have discussed, and they couple it up with a bit of memory that is called shared memory. Okay, these cores can be 32, 64, 128, 256, just a ballpark I'm trying to tell you. This shared memory is somewhere around 48 KB up to 96 KBs. Okay, they club it up and they call this particular unit streaming multiprocessor, in short SM. Okay, now they put multiple streaming multiprocessor, multiple SMs on the die, and they club it up with global memory. Okay, that becomes the entire architecture of GPU. Okay, so in Volta V100, we have 64 cores on one SM, and there are 80 such streaming multiprocessors. Combined with 32 GB of memory, we get Volta V100. Okay, there are a lot of electronics details that, of course, I'm not telling you, but that is how, this is what is relevant to us. Okay, why I'm telling you is that you should be able to gauge, as in if your application would be, if it would be, able to utilize this architecture or not. Okay, if you know this, then you'll be able to gauge if a particular application that you have can be executed, or how it should be executed, so that you can get the maximum performance out. Okay. So next is the GPU programming model. Okay, this is again a very high level of model, but this is what even the simplest GPU program will have. Okay, so first of all, okay, so we have three components. Okay, any data that you want to process has to exist over network or storage. Second is the entity that we are calling host. That is the you can call CPU and RAM combination that you have on the system on which the GPU is existing. And the third is the GPU, okay, on which you want to offload your computation. GPU always works in a master-slave model, okay, and GPU being the slave, okay. Everything that GPU does has to be instructed by CPU, okay. So we'll see how it works. So imagine a very simple application. You want to process an image. Okay, this image 123.jpg is in storage. Okay, it's not in your hard disk. Now if you want to process this on GPU, imagine the resolution is so big that you want to process it on GPU. Okay, so now the first part your program will do is it will transfer the image from storage to RAM. Okay, that will be done by CPU. The second part is to convert that 123 to JPEG to some primitive data type array. Okay, for example, integer array or byte array or any array that you want. And that you have to decompress the image. You need to read the format and convert it into primitive data type. Then you put this data into array which is on GPU. You need to send this array to GPU memory from RAM. The third part is that you instruct that you compute this. You instruct GPU to process this particular input and generate an output. Okay, the GPU function is generally called a kernel. The fourth thing is that you take this output to the RAM. Okay, for you to use it. Because we already discussed that GPU is an external peripheral. Anything that is not in the GPU memory will not be accessible. So to access that, you again bring it back to the RAM, and after that, you can do if you want to save the outcome, you can save it on storage, or if you want to send it to network, you send it to network. Okay, so that's how the entire process works out. Okay, it's so if you have a computation that is running only on this part. Okay, and if you don't have these things, if you don't have a function which is calling GPU, it is going to stay there. Okay, if you and the amount of global memory that is present is also a concern. You cannot, if you have 32 GB of memory, you can't have a model that is occupying 64 GB of GPU memory. Okay, and yeah. So is this understood? Do we have any questions over this? Great. So I'll be giving you an example as to I'll give you a use case that I have implemented, just so that you understand what is the need of it, you understand the scale of it. Okay, so there is something called as document tagging. If you have a particular, if you're working on documents, you want to make sense of those documents. Okay, to make sense of any domain, there is a term called as ontology. Okay, ontology is nothing but set of concepts that governs that particular ontology. So we are working in medical domain. So the entire list of diseases, genes, proteins is our ontology. Okay, in ontology, what happens is you have you have an ontology file which has a set of concepts. Okay, so this is how one concept will be defined. Okay, a concept is going to have some n number of synonyms. So, for example, take lung cancer for instance. So, lung cancer is also known as lung non-small cell carcinoma. It is also known as NSCLC and so many other types. Okay, XYZ 1, 2, 3. We call it disease 1, 2, 3, 4. Okay. Now, I want, when I get a document, if I find lung cancer, okay, I will replace it with disease 1, 2, 3, 4. So that my entire system will understand that whenever I look for disease 1, 2, 3, 4, this document will come back. In document 2, if I have lung non-small cell carcinoma, then I'll again put disease 1, 2, 3, 4. Okay. So this is how this entire process is called as document tagging. The ontology that we have, it has more than 75 lakh synonyms. It has more than 8 lakh buckets. There are 8 lakh concepts and more than 75 lakh synonyms. Okay, so computation, if I have a document, the computation becomes that I have to search for all these small synonyms. Okay, and I have to tag the synonyms that are appearing in that document. Okay, so I do not fire some 5, 10, 50 threads or 5,000 threads. I fire 75 lakh threads to utilize this 5120 cores so that it is completely occupied. And then I get the outcome in 8 milliseconds. Okay, this usually takes around some seconds. It is because we do it on ES cluster, so we have not directly compared it with CPU, but it is at least 8x faster than the entire cluster of ES. And we are using one GPU in that, one Volta V100. Okay, I just wanted you to understand the scale on which we are working. Okay, we are for something to be offloaded on GPUs, we don't need like 5 data elements or 50 data elements or 500 data elements. We require thousands, millions, and we require massive computation to be offloaded. Okay, and that's when GPU computing makes sense. Okay, we have a number of libraries that support us. Megh already told us about at least 3, and like we can use them. But this is how finally this would be utilized. Okay, so that's it for my session. If you have any questions, you can ask.
What kind of changes one is to perform? So one is to upload some computer task dedicated to the GPU.
So you need to understand the underlying mathematics of it. Okay, so take an example. For example, you need to increase the brightness of the image. Okay, that means you have to change the pixel value of each element by, let's say, 5. Okay, so if you have a 100 cross 100 image, that is, so you need to basically do this on entire image, the same operation. So now you know the computation. Fetch the pixel, you increase it by 5, and you write down the route or write down the outcome in the array. So you put that out on GPUs. Okay, or you can use a library that is given by NVIDIA to increase the brightness. But if you are working on CUDA, you can perform this kind of.
Yes. And in that case, if I am using library by NVIDIA,
yes,
if I call the function of
that library,
Yes.
it will automatically detect the GPU attached to the machine and
Yes.
it will
Yes.
follow
Yes.
it all.
Yes.
Right?
Yes.
So it takes the CPU.
I mean, the library will not detect per se, but you have utilities that will detect the GPUs, and before using the GPUs, you can basically test it out whether GPU is visible to the host or not.
Okay, and what if I have something which is bigger than 32 GB, which is a global memory that is
You break your data.
chunky?
Yes. Yes. I mean, now we have GPUs with more than 64 GB GPUs are also there. We certainly procured a much capable GPU. Any other questions, please? Okay. So we'll be starting the high tea and wait. So we have Gaurav has an announcement to make before we start. So Gaurav.
So when we started working on GPUs, we had of course only NVIDIA team to talk to, nobody else. Right? Now we see at least there's quite a lot of excitement around it, and a lot of people talking about it. At least online you can find a few things beyond NVIDIA. Otherwise, it's been only, if you have something, you go to NVIDIA. And that's where we thought that we should have a community. There are communities around the world, but here in this part, there hasn't been really any concerted, consistent effort. And that is what we thought. So when the initial idea of this meetup, when we came up with this idea, then people started registering, and when we had the conversations, the question was, okay, when will be the next one? Honestly, we were not prepared with that. We had just thought, okay, we'll just have one. Let's try this. Let's see, and then we'll think about the next. But now, looking at the response, and there are a lot of people who just said that we want to watch it online and so on. And we have got a response from a few campuses in Pune already. MIT, WPU, COEP, so on. So that's what we see. Maybe we should talk about this being more like a community. Let's dive it, wherein we can have regular meetups. We can have a bunch of people together on this common interest, doing something around GPUs, learning from each other. So that's the idea. So today we launched that. This is the community. So you all are welcome. Please scan it and join the community. And as with all communities, it's not like we are coming up, with this and we'll dictate. No, it's really community. It's all upon you. Whatever we want to do together as a community, we will do. Right? So that's where it is. The purpose is simple. It is really in the end that we should be able to exchange the knowledge, exchange the ideas, learn from each other, and help each other connect with others as well. For example, something where we have worked upon, if we can help someone, or others who have worked on some problems, and if we can learn from them, if we can get their help, and ultimately, as a group, getting more help from NVIDIA itself, right? Because they're also naturally for everybody, the responses also, when they see that yes, there are more people interested, and what are the kind of questions that people are asking, it becomes easier for them to get those resources, to dedicate those resources, or to be more consultant on that. So that's why we see, that's what we are trying to do with this community. Please do share it with your friends, colleagues, wherever. Yeah. let's have everybody coming together who want to learn and do something with GPUs, and we will announce the next meetup in the community very soon. Yeah. Thank you.
So we have arranged the high tea for you guys, and you can also enjoy the posters that our colleagues have built up. The intention being that we can talk about AI as much as we want, AI and GPUs as much as we want, but unless we see that happening in a particular process, it is difficult, right? So you can start having a look at the posters. You can start the
and we want you to ask hard questions.
yes, yes. Okay.
What I guess, can you ready, scan?